Another simple machine is known as the wheel and axle. Remember, the whole purpose of using a simple machine is to gain a mechanical advantage. A mechanical advantage is defined as the number of times the machine multiplies your effort force. 1 is the magic number that all comparisons are made from. If you have a mechanical advantage greater than 1, your effort force is going to be less than any resistance load you're trying to lift. As a trade-off though, the effort distance is always going to be greater than the distance to the load. If your mechanical advantage is less than 1, that means that the machine is not multiplying your force, and instead it actually takes more effort to lift an object, but the trade-off is your effort distance is going to be lower. It's important to remember that mechanical advantage can never be less than or equal to 0. Still, as a review, remember that ideal mechanical advantage is your theory-based calculation, and it's based only on how it is built, so it utilizes the distances or the measurements of the machine. The ideal mechanical advantage is simply the ratio of the distance traveled by the effort force to the distance traveled by the resistance force. You can also use the ideal mechanical advantage to find, in theory, how much effort force is needed to lift a particular load. You would simply take your ideal mechanical advantage that's based off of your distances, plug in the value of the load you want to lift, do the algebra to figure out how much effort force, in theory, should be needed to lift that load. The actual mechanical advantage is an inquiry-based calculation, so it's what you get when you actually try to lift the load. The actual mechanical advantage is the ratio of the force of the load over the force of the effort actually needed to lift that particular load. So let's take a look at the wheel and axle. On the wheel and axle, the fulcrum is in the middle, and then your effort load and your resistance load can vary based on what you're trying to do. The wheel and axle move together as a simple lever to lift or to move an item by rolling. You do need to know whether within the wheel and axle system which one is applying the effort and which one is applying the resistance force, because it varies based again on the task that you're trying to do. Here's some examples of a wheel driving an axle. So you have your steering wheel, the knob on a washer or dryer, or you could have the water shutoff valve. In all of these cases, the effort is being applied on the outside, the resistance is being applied to the axle. Let's take a look at this particular example of a wheel and axle. So we have a 6-inch diameter axle acting on a 20-inch diameter wheel. Both the effort and the resistance forces will travel in a circle if it's unopposed. That means I need to know something about circumference. As a reminder, the circumference is simply 2 pi r, or pi times the diameter of the circle. If I take a look at that in terms of our distance of our effort and distance of our load, the effort could be pi times the diameter of the effort, and again it could be either the wheel or the axle. The distance of the load is pi times the diameter of the resistance. Again, it could be the wheel or axle depending on our situation. If I substitute that in for our IMA, notice how pi cancels, so we're still left with the same equation that we've always used. Using this example above, if the axle is driving the wheel, we're going to take 6 inches over 20 inches, so we're going to get a 0.3 mechanical advantage. That actually means it's going to be harder for the axle to drive the wheel. If I switch that up and the wheel is driving the axle, I get a mechanical advantage of 3.33. So again, it's all about distances in determining the ideal mechanical advantage. If I'm finding an actual mechanical advantage, we need to know a little bit more information about what's actually going on. So take a look at that wheel and axle assembly to the right to solve the following problem. If the wheel is driving the axle, that means the 70 pounds is my effort force, and the 200 pounds is that axle setup. I could take the force of my load over the force of my effort and get a mechanical advantage of 2.86. The efficiency then of this system would be our actual mechanical advantage divided by our ideal mechanical advantage. Recall from the previous slide that our ideal mechanical advantage was simply 3.33. So our actual mechanical advantage divided by our ideal mechanical advantage gives us an efficiency rating of 85.9%. I could do this exact same math with a different scenario, so I could have my axle driving my wheel, and all you would see is the numbers trade places where they're at. Now again, if my axle is driving the wheel, my mechanical advantage is going to be less than 1. This includes our mini lesson on wheel and axles. Please make sure you ask any questions that you may have.